Ladies and gentlemen, welcome to our today's class. And this class is a continuation on the performance of transmission line in power systems, where we had discussed about the short transmission line. We also discussed about nominal T method under medium transmission line. Now I want us to continue with medium transmission line, and the method of discussion today is on nominal pi method. Nominal pi method. Now, in nominal pi method, you find that the capacitance of the line is divided into two equal parts, where the first half is lumped at the receiving end and the other half is lumped at the sending end. So the circuit diagram of the nominal pi method now appears as follows. So just as I have said that the capacitance of the line is divided into two, so you can see that the one half is at the receiving end and the other half is at the sending end. So we also have resistance and the inductive reactance. The current at the sending end is at that particular point. Then we have the current, the line current. We have the current across the capacitors, where we have IC1, then this is IC2. So we also have the load current as IR. Now at the receiving end, there are several parameters that we have. We have the power, that is the receiving end power or power delivered to the load. We have the receiving end voltage, and we also have the receiving end power factor. That will be cos phi r. So just as I have said, we can define the parameters in the circuit. PR is the receiving end power. We have VR, receiving end voltage. We have cos phi r, that is receiving end power factor. Receiving end power factor. We have IR, that is the current at the receiving end, or the receiving end current. Receiving end current. Receiving end current. IL is the line current. IS is the sending end current. Sending end current. We have VS, sending end voltage. We also have the sending end power, PS, sending end power, and also we also have the cos phi s. Cos phi s will actually give us the sending end power factor. Sending end power factor. Sending end power factor. Now from the circuit diagram, there are some equations that I want us to form from the circuit so that From there, we'll be able to move into the phasor diagram. So if you look at the circuit diagram keenly, you will realize that the voltage across the capacitance lumped at the receiving end, at the sending end, will be equivalent to the Vs, because this circuit is parallel to the sending end voltage. You also realize that the voltage across the capacitance at the receiving end will be equivalent to the receiving end voltage. Receiving end voltage, that is VR. Thus, the sending end voltage, just in the next page, we can say the sending end voltage Vs is equivalent to the voltage drop on the line, that is IL times ZL times Z, that is the line impedance. Z is the line impedance, plus the receiving end voltage, which will be experienced on the parallel circuit. That is VR, receiving end voltage, where we are saying that Z is equivalent to the line impedance, and that is R plus JXL. So substituting this one into question 1, can call that question 1. Substituting Z into question 1 will give us the sending end voltage as IL into R plus JXL plus VR, the receiving end voltage. That is question 2. At the same time, you will realize that the sending end current from the circuit, the sending end current is equals to the line current plus the IC2, that is the current across the capacitance that is lumped at the sending end. So that the sending end current IS is equals to IL, the load current, plus the IC2. That is question 3. Now, moving to the other side, the receiving end side, you can see that at the receiving end side, the line current, after reaching this junction, also divides into 2 to give the receiving end current and the IC1, that is the current across the capacitance that is lumped at the receiving end. So that the line current IL is equals to the receiving end current plus IC1. That gives us equation 4. So you will also realize that we can also express IS in terms of the currents, in terms of the receiving end current, whereby we'll say that the sending end current is equals to the receiving end current, that is when you substitute IL, when you substitute question 4 into question 3, it will give us IR, receiving end current, plus IC1 plus IC2. That is question 5. This one is evidenced from equation 3. That is by substituting question 4 into question 3, whereby IL is replaced with IR plus IC1. And that gives us the expression in question 5. Now, from there, we are able to get the phasor diagram. Using the expressions that we have actually formed here. We can get the phasor diagram. So let's now go ahead and get the phasor diagram. Phasor diagram taking VR as the reference phasor. taking VR as the reference phasor. Now, let's have the starting point. That is where we have the starting point, and we are saying that VR is the reference phasor. So being the reference phasor, it acts at an angle of 0 degrees. That is VR as the reference phasor. It acts at an angle of 0 degrees. Now, if you look at the currents that we are having, we have IR, the receiving end current. We have the line current, and we also have the sending end current. You will realize that the receiving end current is lagging behind the receiving end voltage, so that the power factor cos phi r is lagging. Now, by adding a leading current, that is IC1, that's the current across the capacitor, the leading current IC1, the line current IL will lag, but not as IR. So the line current IL is leading the receiving end current by some angle. At the same time, by adding IC2, you will also realize that the sending end current is also lagging, but not as the line current. So the line current is lagging behind the sending end current. At the same time, the receiving end current also lags behind the line current. So we have three major currents. That is, three major currents. We have the sending end current, the line current, and also the receiving end current. So this is the receiving end current. This one is the line current, and we also have the sending end current. Now, if you look at the phasor, if you look at the equations, look at the equation 4, where we say the line current is equal to load or receiving end current plus the IC1. So that means that when we add our receiving end current plus the IC1 should give us the line current. And therefore, the line, it's the leading current. So it's the leading current. It's leading by 90 degrees. So it will be vertically upwards. That is IC1. Then we also have IC2. IC2 comes as a result that when you add IC2, that is a leading current, to the line current, should give us the sending end current, and it can be seen from our phasor diagram. You can see that sending end current is equals to the line current plus the current across the capacitance on the sending end. At the same time, line current is equal to receiving end current, which is phase 1, plus the current across the capacitance at the receiving end. Now, back to equation 2. If the bracket in equation 2 is broken, then you will realize that the sending end voltage will be equivalent to the receiving end voltage plus ILR, which is the current across the resistance, plus JILXL, that's the current across the inductive or the current across the inductance. So that if this is the receiving end, then the current is IL, the current across the line is IL. So we have to draw a line that is parallel to the line current, that is IL. So we have to draw a line here parallel to IL, and that is that. So that this part is now ILR. And you remember that the resistance and the inductive reactance are out of phase by 90 degrees. And therefore, the angle between ILR and IXL is 90 degrees. Is 90 degrees. So that this one now gives us ILXL. And this one gives us now the impedance, that is IZ, where Z is the line impedance, and that line impedance is actually the phasor sum of the IR and the ILXL. Now, if you look at the phasor diagram, from the phasor diagram now, you can see that the Vs can now be obtained, where we are saying that Vs is the VR plus ILR plus ILXL, so that the vector for the sending end voltage is as follows. So this gives us the Vs, and that is the sending end voltage, Now, the power factor, just as I said, that cos phi r is the receiving end power factor, cos phi s the sending end power factor. The angles phi s and phi r can be obtained from the phasor diagram, whereby the angle between VR and IR gives us the phi r. So that the angle between, now you can see from the diagram, the angle between phi VR and IR, that gives us phi r. And thus, if I want to now get the receiving end power factor, it is the cosine of the angle phi r. That will give me the receiving end power factor. The sending end power factor will be equivalent to cos phi s, where phi s is the angle between Vs and Is. Vs and Is. So that angle is phi s. Now, from the nominal pi method, there are also some parameters that we may be asked to get. One of them is the receiving end power, the sending end power. We may have for a single phase, also for a three-phase. So what I'll be having, if I'm told to get now the receiving end power, that will be root 3 VR IR cos phi r. This is for line values. For line values of current and voltage. I may also express the same or get the same receiving end power using the expression receiving end power equals to 3 VR IR cos phi r. But this one is used for phase values of current and voltage. Similarly, sending end power PS is equals to root 3 Vs Is cos phi s. PR is equals to 3 PS is equals to 3 Vs Is cos phi s. Where I'd said that this one is for line values, but this one is phase values. So we talk of line values of voltage and current, but this one is phase values of voltage and current. Now we also have the transmission efficiency. Transmission efficiency Transmission efficiency is actually the ratio of the receiving end power to the sending end power expressed as a percentage. And that will give us PR all over PS times 100%. Now the other parameter that we may be asked to get is the voltage regulation. The voltage regulation. Voltage regulation. Voltage regulation. Voltage regulation, which is actually the difference in voltage at the receiving end of a transmission line under the conditions of no load, also expressed as a percentage. So we talk of percentage voltage regulation. That will be equivalent to the sending end voltage minus the receiving end voltage all over the receiving end voltage, expressed as a percentage, times 100%. Now, that marks the end of the discussion on the nominal T, and in our next class, just in some few minutes' time, we'll be looking at some examples, maybe one example or two on the nominal pi method, so that we apply the expressions that we have derived here into practice. Otherwise, thank you for now, and be